When a missile accelerates to Mach 2.8, the atmosphere stops acting like air and starts acting like a physical wall. The sheer friction generated at nearly 3 times the speed of sound turns the air surrounding the nose cone into a 2,000 degrees Celsius blowtorch. In this environment, standard aerospace materials, like aluminum and steel, melt into liquid almost instantly. This creates a difficult paradox for aerospace engineers. To survive hypersonic flight, a material must be incredibly hard and resistant to extreme thermal shock, but it also has to be flexible enough to absorb massive amounts of kinetic energy without shattering on impact. Finding a material with both of these contradictory traits seems like a distinctly modern engineering problem, but the specific metallurgical logic required was discovered over 2 millennia ago by ancient Indian blacksmiths. The structural architecture required to survive these conditions has existed for 2,000 years, hidden within the microscopic grain of medieval steel. This image shows a Damascus sword. Forged from Indian wood steel, these blades combined properties that usually exclude one another. They were hard enough to slice through armor, yet flexible enough to bend without snapping. For centuries, the exact method used to achieve that dual strength and flexibility remained a mystery. It wasn't until scientists examined the steel under modern electron microscopes that the microscopic physical mechanism became clear. They found that ancient blacksmiths had inadvertently engineered carbon nanotubes and cementite nanowires directly into the metal. This schematic illustrates the ancient casting process. Melted ultra-high carbon steel was poured into copper forms and rapidly cooled in cold water, initiating transient nucleate boiling. By managing the cooling at this boundary layer, the metal avoided cracking. Instead, impurities clustered into microscopic, energy-absorbing bands. Looking at this micrograph of the steel's internal structure, you can see extremely small spherical carbides distributed throughout. These tiny, hard particles acted like a microscopic saw at the cutting edge, giving the blade its immense strength. By mastering this intense thermal process, ancient swordsmiths successfully practiced nanoscale structural engineering centuries before the microscope was even invented. Let's fast forward to modern aerospace engineering. This is the BrahMos missile, and to survive sustained flight at Mach 2.8, it requires a highly advanced thermal protection system. The solution protecting this airframe is a specialized ceramic composite made of zirconium diboride mixed with silicon carbide. This composite uses weave patterns and nanofillers to create an interface zone. When intense heat strikes, the grid conducts thermal energy horizontally, protecting the core. Simultaneously, flexible nanofillers compress to absorb kinetic shock waves without fracturing, replicating the Damascus sword's structural logic. This multi-layer protection distributes both heat and kinetic energy across multiple surfaces. The external ceramic shield takes the abuse, preventing concentrated damage from reaching the internal guidance electronics and fuel systems. From the medieval forge to the hypersonic lab, the underlying principle is remarkably similar. By layering materials at the nanoscale, engineers can force a composite to absorb energy that would otherwise destroy its individual components. Indian engineers validated the viability of these ultra-high-temperature ceramics by subjecting them to intense plasma wind tunnels. This aerodynamic test model is being exposed to conditions reaching 4,000 Kelvin, proving the ceramic composite can survive immense thermal shock. Surviving testing environments that severe places India in an elite 5-nation club capable of deploying hypersonic thermal shielding globally. This modern achievement shares a direct lineage with the creation of wood steel. Both represent a mastery of extreme temperatures and advanced composites, developed on the exact same subcontinent thousands of years apart. The push to master extreme thermal and kinetic forces creates a clear continuity between these ancient methods and our current aerospace goals. The material science enabling our future in the skies is a modern extension of metallurgical breakthroughs from our past. We are not just inventing new solutions, we are evolving ancient ones.